Oh, absolutely. Excellent.
So today I'd like to talk about solving one Laplacians, which is a slight generalization of the regular Laplacians, which is a zero Laplacians. And unfortunately, we can only do this in very special cases for complex, simplicial complex. But of course, we can do it fast, given enough restrictions. And the co-authors are Michael Cohen, Brittany Fossey, Amir Nariri, Richard Pang. And there's another person I'm missing here, that's Noel Walkington, which I just found out about, but I'll have to change the slides afterwards. Okay, anyway. So all these things really boil down to simply solving regression, right? So regression is you have some data, and you'd like to fit it with some kind of curve, say a line, and then the goal is to fit that data, and I claim that Laplacian solvers are no special thing. That's all they're doing under the hood. So in particular, right, remember that if you have an over-constrained system, you want to solve A equals B, and in general you can't solve it, so what do? You multiply both sides by the transpose, and then you solve this system, and magically the system A transpose A is now symmetric and positive semi-definite, and so this is what makes a lot of this stuff work, okay? And so, of course, the big question, and there's a huge amount of work in this conference related to this problem, and that is can we eventually solve the general case faster? And there's sort of all the usual starting points on that is how do we at least reduce the number of rows? And so there was all kinds of nice work on that, okay? So in particular, the case, the standard case we've been looking at in these talks so far is what's called symmetric diagonally dominant. And what that corresponds to then is a symmetric matrix for which for every entry the sum of the off diagonals is less than or equal to the diagonal, okay? And so these actually have a nice correspondence. Every non-zero entry off the diagonal simply corresponds to an edge, and it's simply the negation of the weight of that edge in some sense. Okay. So then there's a huge line of work on how you solve these, starting, in near linear time with Spielman and Tang, and then some work with Janus and Richard, for which we got down to a single log. I think an important point to point out is that not only can we solve these things fast sequentially, but we get near linear time algorithms which also work in parallel. So it's not clear how much parallel you need, but at least, so a lot of nice problems, like the simplest question is how do you find the, single source shortest path in a possibly negative weight graph? It's not clear how to do that without going through graph Laplacians efficiently. And so those are all special cases for which, these solvers can be applied. And so, of course, the state of the art is this nice work of Richard and Dan where they show that, in fact, not only can you do these in near linear time, but you can do polylog depth. So in other words, you can throw out billions of processors at one of these things without any problem. You just have to buy the processors, but ignoring that problem. Anyway, so that's what we know. And then, of course, there was another paper with too many authors to list here, for which we got it down to a half a log. Okay, and so let's go on. So there's another whole approach which we ended up using for this, which is related to this work of KOSZ, or what they showed then and Leith, so that, in fact, they don't get as fast a solver, but they solve a very interesting problem, which is solving symmetric diagonally dominant or graph Laplacians as an energy minimization problem. So it's a simple convex problem, and magically that's just a very nice way to see the world. And whether it's better or not, but it looks like it generalizes nicely in what we'll talk about. Okay, whoop. So how should we think of Laplacian? Well, eventually I'm going to want to go to higher dimensional topology, so I'd like to recouch graph Laplacians in terms of very simple topology so that we can then generalize it to higher dimensional topology. Okay, so the simplest is you look at a matrix, which I guess I'm calling B transpose for some reason. Many people call it just B. But I claim for topological reasons it's nice to think of it as B transpose, and then B stands for boundary. Okay? So what it is, it's a matrix, right, so that every column corresponds to an edge, and then it has two entries for the two endpoints of that edge, one plus and one minus, and that corresponds to this kth edge. But actually, if you go ahead and you just put two ones in that really doesn't cause a problem. All that corresponds to is symmetric diagonally dominant systems. So in general, you can simply consider these boundary operators. For us, we won't actually go back and consider this case, but just to point out that that's really the only distinction, is whether you allow both two positive entries or not. Good. So then, rewriting the graph Laplacian problem, instead of using the usual b, from now on we're going to use these partials, and we're going to rewrite this, right? So now what happens is the graph Laplacian problem is, what you do then is you take this boundary operator and then you transpose it. So this says we should go from vertices back to edges. From edges, we should multiply by some physical quantity, like the conductance, and then multiply back to get some kind of residual at the vertices. Okay, boundary operator. And if you want, it's nice to think of writing this way, and so therefore really all we've done is we can sort of ignore this constant, but in general throughout the rest of the talk, let's assume that all the conductors and resistors are 1. Okay? Good. And so then just rewriting this equation says we want a voltage, so that when we convert that to a flow, then that flow has the property that when you convert it back to a residual at the vertices, it meets your demand. Okay? And this is exactly the regression problem we started with at the beginning. So in some sense, we really are just doing simple regression. It's just that we've restricted ourselves to a very special kind of matrices for which we can do it faster. Okay? That's all that's happening, right? Good. So the important thing here is that partial 1 has at most 2 non-zeros per column. So its factor width is called 2, right? So it's a very beautiful paper by Dash and Spielman, I think in 2008, for which they show that you can solve any factor width 2 problem quickly. Okay? That's a very nice result, which I don't think is well known and should be. But anyway, it's a very beautiful piece of work. Okay? So, of course, the big open question is, can we ever solve anything besides factor width 2 fast? And, of course, it's not clear. I think there were some people, I think Aaron and Tat, claimed that they could, but I think, not sure of the details of the proof, that, in fact, factor width 3 is sort of complete in some sense. But I'm not sure. It'd be nice to see that. Looks something like the reduction from general CNF to 3 CNF. But it'd be interesting, but I think there's some problem with the number of variables when you do that. But anyway, so what we'd like to do then is the whole point of this is to try to wander off and look at problems of factor width more than 2 and see if we can still solve them. Okay? Good. So there's some work in this direction. Bowman, Hendrick, and Mabasa said that, in fact, you can solve any elliptic finite element problem by reducing it to basically a factor width 2 problem, preconditioning it. Okay, so this is for special cases like the heat equation and stuff in higher dimensions. And then Dash and Spielman looked at linear elasticity. I'm not exactly sure what headway they made there, but they at least, again, tried to look at higher factor width problems. Okay, so what generalization are we going to pick here? What we're going to do is say that really what we have is our graph really consists of vertices and edges. These are really just 0 and 1-dimensional simplices. So we'll now introduce 2-dimensional simplices and maybe even 4-dimensional simplices, and we'd like to solve the equivalent problems. Okay? Good. So that's the whole goal. Good. Okay. So then what I'm going to do is actually, so to rewrite this, so when we say Laplacians, the topologists would say those are 0 Laplacians, and what we're going to look at today are what are called 1 Laplacians, which is 1 higher dimension. Okay? Good. And this is all related to this thing called Helmholtz-Hodge decomposition, which we can all view as just related to the question of whether your flow in a graph is a circulation or a potential flow. And really that's the same thing. Okay? Okay. And then we'll talk about what cases in the 1 Laplacian we can handle, and then we'll discuss the linear time algorithm. Good. Okay. Good. So why higher dimension? So let's just do the first simple case, and of course, which is going to motivate the stuff that topologists do anyway, and that is really related to Navier-Stokes, for which you have a curl. Probably the easiest to think of Maxwell equation, in which you have electromagnetic radiation in the right-hand rule, which says if you have a current flow, this gives you a magnetic field at right angle. So what happens then, how do we then formulate this as a discrete version of that? And so that's what the goal is. This is you should just keep in the back of your mind that really we're trying to do some kind of thing where we have some kind of right-hand rule, okay? Where a flow through a triangular face is going to induce a circulation on its edges, okay? And we're just going to formulate that and then try to solve that, okay? And then whether this solves Maxwell's equations, that's not so clear, but it should be useful. I mean, there's a bunch of restrictions that we can't do that we don't understand. Okay. And then later on, what I'd like to do is talk about why that may be related to social networks. Okay, good. Okay. No, we just did. Okay. So let's redo the zero Laplacian. So the thing that we're missing then in order to understand that is you really need a boundary operator that goes from 0 dimensions to no dimensions, okay? And so in that case, it ends up being very simple. It's just let's assume that, remember, we have, for a Laplacian, we think of this as a graph. And so therefore, let's assume the graph is connected. Otherwise, it's slightly more complicated. And then what happens now is I claim the boundary operator is simply just the all ones operator. It simply takes your vertices and just takes the sum of the values at the vertices and returns that sum, okay? This gives you a natural operator, which we end up calling down, which the topologist called down. And the reason is because you start with something of dimension 0, you go to something of dimension -1 or whatever, and then you go back up to dimension 0 again, right? So in our case, this is just then a matrix of all ones, right? So this is a big, dense matrix. And then there's the up operator, which is our standard Laplacian here. And then when you combine them, you get the nice property. This is then called the zero Laplacian, and this is the mix of the two. And why is this nice? Is because this now is non-singular, okay? So the beauty now is we've sort of, in a clean topological way, allowed us to handle the null space problem, which we didn't, if you notice, we always do in a sloppy way. We sort of push it under the rug. Okay? And that's what the topologist tried to do. And in higher dimensions, that's going to be important. Okay? So then, of course, now let's understand this in a very pedantic way. So how do you solve this equation now? Well, you have a V, a potential or a voltage, and you're trying to reach some residual. So again, what you do is you say, well, D can be written as a direct sum of an up and a down, where the down is simply returns, I guess there should be a superscript here, it simply returns the sum of the values at the vertices, right? And so that should be, that's how much we should remove from this. And then when we remove from that, that gives our D up, and then we just solve this equation, right? So this is just the classic thing we always do, right? You simply remove, you make sure that the demand has the property that the sum of the demands is 0, right? And this is just a pedantic way of saying that, right? Okay, good. And so that's what we want to do. Good. Okay. Right? And so what makes all this work is this very nice property that if you take the boundary operator 1 and then apply the 0, you get 0. Okay? So in particular, this is equivalent to saying that the kernel of this map contains the image of the other map, and in particular, in our case, when the graph is connected, we get equality. Okay? And so all this stuff really is very fancy, but you know, if you've taken Strang's linear algebra course, which I think is required at MIT, and you look at chapter 3, this is what's called the 4 fundamental subspaces theorem. Okay? So it's all very simple stuff. It's not really anything fancy. Okay? Good. Okay. So from now on, we're going to have simplices, 0 and 1, 2, and 3-dimensional. And we're going to use names, vertices, edges, faces, and cells. And so in general, we're going to have some kind of triangulation. So our triangulation is going to be some messy thing that looks like this here, right? So it's going to have edges, vertices, and tests. Okay, good. So then what we want to do, let's start using fancier terminology. So a zero chain then is a map from vertices to the reals. So this is the one we talked about, the partial operator. You have values at your vertices, and it returns, in our case, simply the sum of the values. You have another operator that takes you one chains, which takes you from I guess these are just scalars. So it just simply assigns values to the vertices. This one assigns values to the edges. And then we'll have another one that assigns values, real numbers, to the faces. Okay? And then you could imagine similarly for tests. And so quite often we call these potential, voltages, or residual flows. These are flows. And then we'll call these fluxes. Because the way we're thinking of this, right, is we're thinking of the value here being how much flow or electric current flows through this triangle, right? So, good. Okay. And then we have operators that go between these, right? So, in particular, then our partial 2 then takes us from 2 chains to 1 chains. Partial 1 takes us from 1 chains to 0 chains, right? This is all sort of standard. Good. Another nice way to think of this is really you have a post set, you have a complex, and you have a boundary operator that takes you from top to faces to edges to vertices back to the components, right? Good. And so we have these nice maps here. And now the critical fact is that we're required when we set up this map that this property is true. That remember we have this plus or minus 1s running around on the edges, and throughout the whole map we have to decide on the right sign, and the critical thing is to set it up so that this is actually true, so that everything works, right? So this is required of us, right? Good. And of course that's equivalent to saying this. Good. Okay. And so then the question is, there's a slight question here is when we put one of these chains on the right-hand side, should we call it residuals or demand or potentials, right? And when we put it on the left-hand side of an equation, let's call it a flow. Okay? Good. So then what is partial 1? Well, again, it consists of 2 parts. It consists of a down operator. So what's this, right? So this says you take a flow on your graph. From that you compute a set of potentials, and from that you generate a flow. Okay? So this takes you from flows to flows. This says the same thing. This says it takes a flow on the edges. It returns fluxes on the faces, and from the fluxes on the faces it returns back a set of flows on the edges. So both of these operators then take you from flows to flows. Okay? Good. And of course these are very different because notice that this is a potential flow where this is a circulation. So the reason we're dividing these up very carefully is that this operator is computing the potential part of the flow, and this operator is looking at it, and this operator is looking at the circulation part, right?
These are
and so,
projection maps.
Sorry?
Projection maps. The first one I believe is the projection map.
Say it again.
It's a projection map.
So these are. Yeah, so these are also, you're saying that the image is determined by this, right? So no matter what you put here, you're only going to return a potential flow, right?
It's a projection to the flow space.
Yeah, so it's going to give you into the flow. So you can also view it, right? So it's projecting, right? And so we need to...
What is this second one?
This one here, right? So let's see. I think I have more slides. Let's see. No, let's... So what this is doing here, right, is it says, this operator says, the way to think of it is you have some kind of triangulated space, and you have a flow on the edges. So that flow on the edges is going to induce a flux on the face, right? So what happens then is if you have a triangle here, and I put some number of units of flow alpha on this edge, that's going to induce a flux of size alpha here, right, for the unit case, right? Okay. So, the other way to think of it is, physics, which I should really understand, right? It says that if you have, right, an electrical flow on the edges, that's going to induce a magnetic flow, right? Good. And then on the other hand, once you have this magnetic flow, so then what's going to happen now, that's going to then induce some other stuff here. So you're going to get some beta. And then what you're going to do then is combine these back to get something on this edge, right? So just very similar. So topology, so it's just, I claimed mechanically what we did for graphs. What did we do for graphs? We did exactly the same thing, right? We took a potential, a value on the vertices. From that we generated a flow on the edges. From the flow on the edges we returned a residual. Right? Good? And so that was...
Quite a projection, that delta...
Well, I think
that one down, it can't be a projection.
Yeah, let me. I think what we want to do is do a projection. Let me just go on. So what's going to happen is what I want to claim is this is what's true, right? And that is if you look at the image of these two operators, they're orthogonal. right? And I claim in the case whatever this means that if beta is 0, this is the Helmholtz decomposition that we get that in fact is the whole space. So in some sense, they're projections, right? I think in the end these are right.
They weren't in the lower dimensional case, so.
Yeah, so let's see. I think that we were required to do the projection before we started, right, in some sense, right? We removed the part of the potential which didn't sum to 0, and then we went back and solved it. So that's what's going to happen here. So what we're going to we'll do is we'll do some kind of projection. So another interpretation to this is what's really happening here is that the image of this thing here, of course, is contained in the image of this map. But notice that this map has the property that it returns the circulation for each face. So it's a sum of circulation, so it is a circulation. So this returns some kind of circulation on the edges. On the other hand, this operator here returns something that's a potential. And in this case, we get, I guess, all potential flows, right? So what's happening here is that it's decomposed. These things are returning these two different types. So what's going to be crucial then is that we can break the solution up into solving two separate problems, right? The up and the down separately, similarly to what we did in the zero Laplacian case. And so that's what's going to happen, right? Okay. So there's a very nice exercise to give in a graph theory class, and that is that if you take all the flows on a graph, that in fact you could look at those that are circulations, and those are in fact orthogonal to potential flows for unit size resistors. And in fact is another nice exercise to show that in fact it spans all flows. So the set of all flows can be written uniquely as a potential flow and a circulation, which is sort of a fact that somehow gets used, but somehow I don't think we prove it directly usually, right? But anyway, so that's what's going to make this all work, right? Is really we're decomposing these flows into two kinds, right? Good. Good. So let's go back to the KOZ algorithm. So what do they do at a high level? What they do is that they solve a dual problem, right? So they're trying to find a zero potential. Sometimes I put zeros here for whether that helps, right? To meet some given demand or residual. And so the way they do that then is they solve this dual problem, which they say, I'm looking at all flows which meet the demand, right? So I simply replace this term here with the flow. And I look for that flow, and then I just ask for one of minimum energy. So it's a classic Thomson's principle or whatever for electricity, right? So instead, they just solve this problem instead. Okay, good. And they do another sort of very simple trick, and that is they say, okay, I want to solve this problem, so how shall I do that? Why don't you just start by finding any old flow that meets the demand, and then why don't I then just add a circulation until I minimize the energy? So at a high level, this is a KOZ algorithm. So then all they have to do then is of course, they have to figure out how they're going to do this, but ignoring that for the moment, then they just solve this, right? They find any old flow, and then they try to find one of minimum energy. Okay? Good. And so we're going to try to use this same piece of technology, idea. Okay? So for ours, we're going to do the same thing, right? So what do? First of all, we want to solve this equation. So what do we need to do? So by the Helmholtz, what we do is we first of all wanted to break our demand up. So of course our demand here now is a flow. So we want to break our flow up into a circulation and a potential flow. Okay? So, and so what we'll do is we'll do that. Let's worry about that later. And so once we figure out the circulation part of our demand, then what we'll do is we'll find any other flux on the faces which meets that demand. And then what we'll do is we'll cycle through all those fluxes which for which we minimize the energy. Okay? And so that's going to be how we're going to go about solving this, right? What we're going to do then is just apply KOSZ idea, and that is find some flux which meets the demand. It may not be a min energy one, and then we'll simply then add in more flux to try to minimize the energy. Okay? So it's just try to just do their trick over again in one higher dimension. Okay? So, but the first thing we need to do is we need to take this demand, which is an arbitrary flow, and we have to write it then as a decomposition into a circulation and a potential flow. This is very classic, but let me just go through that. So this is where the projection would come in, right? So the first we need to compute, let's compute the down part. Okay? So I claim when you work that out, that's just a simple projection operator. Right? You simply then compute, you take your demand and your flow, right? And then you convert it to a residual. Then you apply the inverse operator and go back. This is just a classic formula for projection operator. So I claim when you do this, but of course, this inner term here, the only hard part is solving this system. And that, of course, is just a zero Laplacian, which we know how to do. So therefore, we can do this, right? So then quickly, we can figure out how to compute d down. And then if we want d up, well, then we just, assuming there's no error, we simply subtract this from our d. Then that gives us our d up. So we simply then do a very classic thing of decomposing our demand, which is now a flow, into a circulation and a potential flow. Good? And then we just solve the two problems separately, right? Good. So then the hard question now is, okay, so now we have our circulation, and we need to then go back then and find some flux which meets this demand. So the interesting problem here is topologically this all of a sudden becomes quite interesting. Because in the 1D case, what do? We simply take a spanning tree, and it's very easy to see that you can always find a flow on that spanning tree which meets a given set of demands at the vertices, simply because it's a spanning tree, and it basically you can apply Gaussian elimination, right? It's upper triangular, right? It's what's going to be here. It's going to be very hard, and what we're going to have to do is there's very few theorems known about this, but there's a very nice theorem of Chillingsworth who proved that if you have a complex 3D simplicial complex, that in fact there is a way to do it in that case. It is what's called collapsible. Okay? And so that's going to allow us then to find some flow that meets the demand. And in some sense, that seems to be the hardest part of this whole thing. It'd be nice to have some better ideas for that. Okay. So suppose that we have found some flux that meets our circulation demand, right? Good. Did I skip a slide? Whoop. Okay. Good. So then how are we going to do this? So suppose we found some flux that meets our demand. Good. So now what are we going to do? So now we're going to look at all other fluxes, okay, subject to this condition. But I think this condition is trivial no. So now we're going to look at all of the fluxes for which it's zero, right? So which it produces a zero flow. And we're going to try adding this to our system to minimize the energy. Okay? And then it's not too hard to see that this is equivalent to our original problem. Good? But now we'll use a simple trick here, at least to make it work in this case, and that is to say, well, let's assume that we are in some kind of place where beta 2 is 0. In other words, all we're saying is that it's the case that we can pick up all flows, all circulations, as some combination of fluxes. Okay, so that's what beta 0 says. It just says this. Well, assuming that this is true, then this simply says that this flux can be obtained in one higher dimension by just looking at potentials on the tets, such that when you apply partial 3 to it, you get that particular flux, right? So let me just draw a quick picture here. So So that's just simply saying the following, right? And that is, right? We're trying to get some kind of flux coming out of this face here. One way to get that is what we do is we have some kind of value inside here, say heat, and then we just apply that, and that gives us then fluxes on all the faces, right? Coming out. So what I'm assuming here is that we're able to obtain all the fluxes, right, with zero, with this property, as simply having potentials on the tets.
So this means assume that there is actually a bunch. What you start with is a bunch of tetrahedra.
Yeah. So we're assuming, for simplicity, what we're assuming now is that we have a 3D simplicial complex, and so not only that, but on these tets, we're also given. So the tets are nice in the sense that, right, we can generate that this is true, right? Namely, that if you look at all the fluxes for which they generate no circulation, right, that those can be obtained as simply applying, having a, pressure or whatever inside each tet.
So does that correspond to this being simply connected?
Yeah, I think it corresponds. So in our case, let's do the simplest case, is that it's a simply connected ball, right? So, for instance, it's a ball, right, of tets, right?
This is what's usually called homology in topologies. We're saying the homology is trivial.
Yeah, so I think the equivalent to saying the homology is trivial, that it's basically a ball. Okay.
So does Betty 1 = 0 say that a graph is a tree? Is that
Connected.
it's just that it's connected? Is that all? Okay.
Yeah, so
The cycles.
So it only makes sense to talk about it at the level where, it doesn't make sense to talk about a tree, whether the homology there, until you introduce what the faces are.
So I think beta 0 corresponds to connected, beta 1 corresponds to that it's something that looks like a sphere, right? And beta 3 corresponds to being a ball. Right?
Yeah.
I think the Betty numbers are just the different kinds of cycles you can get on a surface. So a ball is Betty number 0. If you get the Betty number to be 1, you get a torus. So you have two kinds of cycles that you can't melt one kind of cycle into the other kind, and that's what. So it's just tracking overall global structures in this shape.
So assuming that we have all these properties, which would be nice to get rid of, then we can now go back and make the following substitution in this equation. We can substitute in here this term here into this equation and try to solve it, right? So now let's assume that we have a flux which meets our demand, circulation. Let's assume that Betty 2 is 0. Then really we're trying to minimize this equation. Okay? Good. And what I claim then is that minimizing this corresponds to solving an equation that looks like this. Okay? For some D3. Okay? So let's see that. That's sort of trivial. So we're trying to minimize this term here. I'm not sure this is necessary, whether this is confusing, but we just expand this product here and we get 3 terms, right? We're going to get a constant term, we're going to get a linear term in F3, and we're going to get some kind of quadratic term in F3, right? If we compute the gradient for these things here, of course, this is going to go away. This term here becomes just a constant. This term here becomes linear in F3. And so if we set this to 0 now, we're just trying to solve an equation that looks like this, where D3 is this term here. So I claim that solving this thing, so if we're trying to minimize this, all we need to really do is be able to solve equations of this form. Right. Is that too fast or not necessary? Wasn't clear. I'm sure it's either.
Confusing me. To do the one Laplacian, you don't need to go to solving an equation on faces. So why to do the 2 Laplacian do we have to go to solving an equation on?
Oh, because we're going to dualize it and claim we're back to 0 Laplacians.
Oh.
because that's all we know how to do. I mean, our problem is that in some sense we did a Fourier, we wandered off in this direction, tried to prove something interesting, and then what we did is cobble together as much as we could so that it was publishable, right? So I mean, that's the way to think of it at a high level, right? And that worked. So that's. But still, on the other hand, you know, somehow, if you're going to go off in this, you need to say something interesting. Otherwise, they don't let you publish a paper. But it's still, I think, non-trivial, right? The people that do, you know, physics and stuff like that, simulations, they had never seen this before. Okay, so that's interesting. Okay, so did everyone agree then that if we go back then to doing this, if we want to solve, if we're given, right? So if we're given a flux that meets our demand, and we're trying to minimize this equation, it suffices to simply solve something that looks like this, right? Well, what does this correspond to? This corresponds to, so what I claim is that if we have a 3D simplicial complex, that if we're trying to solve this just dualizes, right? Because what is this? This simply says we have the value in the middle of every tet, right? And what are we trying to do? We're trying to generate values. So what does this say here, right? This says we have the value at each one. We need to then find values on all the faces. So those correspond to edges. So maybe just try that as a dual here. Right? So we have this picture now that looks something like this, right? There's this tet, right? And it has a dual, the vertex inside going out through each of the faces, right? Coming out here, and there's another one here somewhere else, right? So there, under the hood here is this degree 4 vertex. And what are we trying to do here? We're trying to find values here. We're trying to find a value here at these guys, right? Which have the property that when you view that as a flow on these edges, right? That's this part here. And then you go back and you take those flows and you look at the residuals at the vertices, you get what you wanted, right? So this is precise. This, if we dualize it, is this equation here. So we're back to where we started, and then we can use the same hammer, right? So then the hammer then just says, oh well, since we've made a huge number of assumptions about being a 3D simplicial complex and all kinds of other things, magically it boils back to something we know how to solve. So there's just a zero Laplacian, and then we're home free. Okay, good. But so the interesting point on all this, so this is all nice. You know, we threw in a lot of assumptions. It'd be nice to get rid of those. But we still have this other interesting problem here, and that is how did we ever get any old flux that meets our demand? And unfortunately, that ends up being interesting. Good. So it was a whole work in the 50s by Whitehead on what's called collapsible complex. Okay? And so there's a thing called edge collapsing. So an edge collapsing is something we see all the time. So if you have some kind of graph with a vertex of degree 1, good. A collapsing then topologically simply says you remove the vertex and the edge. But the way we'd think of it is you're in the middle of a solve. So you have some residual you'd like at this node, and you have a single edge here. Well, the only way you're going to get that residual there is by applying the appropriate amount of flow on that edge. So therefore, topologically, you can think of doing this, but under the hood, you can think of it as you're in the middle of trying to figure out the flow on that edge to meet a given demand. Good? So equivalently, you can do the same thing here. So suppose now you're trying to have a given circulation on the edges of a triangulation, and you're trying to figure out how much flux to put on the faces to meet that demand. Well, if there's only one edge on this, if there's only one face common to this edge, the only one that's going to give you the flow on this is this face. So therefore, you're forced to set the flux here to be equal to the flow you want on that edge. And then when you remove it, of course, then you have to update it and readjust the demands on the remaining edges, but you can keep going in that fashion. Okay, good. Okay, so of course you can do the same for solids, right? If you have, for instance, you're trying to get a given flux on this face, and it happens to be only common to a single tet, then you can simply you have to set the value in that tet to meet the value you want on that face, right? Good. So, but this lends itself to a very nice topological question then, is, when can you take some kind of topological structure and get this to happen? Okay? Good. Okay? Good. So there's certain kinds of things that are collapsible. So in particular, this here is a collapsible. It's a tree. This is also collapsible. If you check it out, you can just go through and remove them all. This is not, right? If you're missing these faces, you can't collapse this. Okay? Good. And of course, what would happen then, of course, what does Lorenzo and crew do? They would say, well, of course, you wouldn't keep all these edges because you don't need that many in order to meet the demand. You would just take a subset of those edges which formed a tree, and you would use that. You would jettison the extra edges, right? So the question is, how fast can you decide whether a 3D simplicial complex is collapsible? And also, how do you determine if it has a subcomplex that allows you to meet the demands and is still collapsible?
What's the difference between us two?
Sorry?
What's the difference between us two?
Between this one here, this has a gray here, and this is white.
I saw that.
I know, I just couldn't resist. Sorry. So that means that this is a triangle in the complex. This is not a triangle in the complex.
You don't have the face.
You don't have the face. It's missing.
You don't have face.
Yeah.
It's just skeleton, right?
It's just a skeleton, right? Okay? That's the distinction. Thanks. Sorry. Okay. So how do you even decide if it's collapsible, let alone whether a subcomplex, right? Well, it's NP hard to, in general, for 3 complexes. There's a whole crew of people that worry about this stuff, and they have all kinds of negative results. So the question is, of course, how to get positive results. That seems to be harder. And there's a bunch of NP hardness results in this way, right? It's open for 3 balls, right? Whether you can decide, okay? But there's a very interesting result from way back in the 60s that said that if you have a convex triangulated body, okay, so in other words, a bunch of tets which have been glued together to form a convex body, then that is actually collapsible, right? And it's actually non-trivial. The proof is quite clever, actually. You have to actually do something to make sure you don't get in trouble. Because remember, we didn't say anything about what the shape of these tets are, right? This is an arbitrary mess.
That means that if you have any simplicial decomposition, proper simplicial decomposition of a simple lattice.
Yeah, of a convex simplex, right? Take a convex polytope in 3D and triangulate the interior, right? Then that's collapsible. That's what this theorem says.
I see. Any
Right. And the reason it's non-trivial is because, you have to be careful what order you do this, right? So, of course, you would start by removing some outer face and the tet it's common to, but you have to be a little careful how you do that, right? But anyway, he was able to show that works, right?
So this is a topological result, so it's not obvious to me why convexity is important. Is there an interpretation?
Yeah. Yes. But if you go through the proof, it comes in in the way he does it, right? He has to be very careful.
So there was time when I was talking to Herbert when Adelsberg about those slivers. He said, often if the sliver float to the boundary, then it doesn't matter anymore. It's related. You can somebody pure it up.
I don't know.
So by the way, note this is not a purely topological thing, right? You can have 2 simplicial complexes that represent the same topological space. And one of them is, for example, 3 balls. That's one topological space. There are lots of triangulations. And one of them can be collapsible and one of them can't. So it's a kind of like combinatorial property too.
Yeah, so combinatorial topology, I guess I was assuming by topology we meant combinatorial topology, right? But if you're not, then it's different, right? So that's not so clear. Okay, good. Okay. So, and I guess as we just said, this is all correspond to Gaussian elimination, right? So it in fact has a nice interpretation. So of course, when if in the middle of this thing here, when we're applying this operator when we remove an edge, right? This corresponds to doing some kind of a Gaussian elimination, right? And notice when we do this and we drop a face, what we're really doing is dropping one of the columns in the matrix. So it has a very simple interpretation, because these are higher dimensional in the particular case we're doing, right? So they have very natural interpretation. Okay, good. Okay. So now there's sort of the question is, just in case you hadn't thought about this, there's the obvious simple cases to work out is what happens if you have a triangulated sphere. Okay, so if you take your favorite sphere and and it's been triangulated for you, right? So that there's these triangles, right? Good. So this is one of the complexes. Okay. So then what I want to claim is that, of course, it's not collapsible as the whole thing goes, right? Because there's no edges that are on a single face. But if what you do now is you remove one of those faces, right, then it becomes collapsible. And also it's not too hard to prove, it's a nice exercise, using Euler's formula to show that, in fact, the remaining faces have the property that they generate, their circulations generate all circulations on here, right? So it works out just perfectly, right? Good. So then the next interesting question is, what happens if you take something like a projective plane? So, and this is a nice exercise also to work out. I think Nathan Lineal was playing with this stuff for some other reason, and you end up with a similar kind of thing. So in case you forgot what a projective plane is, projective plane is where you take a disk and you identify opposite points. So for instance, this is x, x, y, y, z, z. Okay? And now what happens here is this is a nice triangulation again, same as before, but unfortunately you don't have enough triangles. So what happens in this case, if you work it out, you need all the faces to get all the circulations. You can't throw any of them out, and if you don't throw any of them out, it's not collapsible. Okay? So this gives you one that's sort of stuck. I think there's a simple solution. You just take the double cover of this, and then you work in some higher dimensional, similar to the symmetric diagonally dominant systems, but I haven't worked that out. Okay. So it's interesting that very simple things happen. There's all kinds of other much more complicated things. There's things that Dunce had and all kinds of other topology things that are much more complicated. It wasn't clear. Okay, good. So in the last few minutes, let me just claim that, most of us here are not really that interested in doing physical simulations because there's slightly more money in other things like social networks and all. So let's try to maybe sell this as a social network thing. Okay? So the first cut. So I claim that triangles come up quite often in social networks. There's a huge number of papers on this whole area of finding all the triangles in a social network. Magically, this is very useful for all kinds of reasons, right? There must be 100 papers on, first of all, counting triangles, but also why you would want to know the number of triangles. And this somehow tells you all kinds of things about a social network. Okay? So that's the first thing. There was actually papers by Target and crew where they showed, and I think Jakob, one of the students when he worked at Facebook, said that in fact clustering based on triangles seemed to give better results. In other words, what you do is you start by taking your social network, you find all the triangles in it, and you glue two triangles together if they share an edge. And then you use that to cluster. And as I understand, I don't think there's any proof of any of this, that somehow gives a much better way of doing social network clustering. Okay. Okay. Recently, there's a student, Babas, who showed that. So the other question is, what you'd really like to do in social networks is find cliques. Well, first of all, chances are there may be an edge missing in some large clique, and so then it's not any longer a clique. But so what you'd like to do is find something that looks like a clique. So the simplest, of course, is what you do is you try to maximize the number of edges to vertices in a subgraph. Unfortunately, that gives you things that are too big. So what he did is he went back and he said, well, let's count the number of triangles to the number of nodes in a subgraph. And magically, that gives you something much better, and it's still computable in polynomial time. Okay? So those are all things that are well known. Let me ask you a question that I don't know and that I think would be interesting. And that is, are the eigenvectors or values of our one Laplacians of social networks useful? And there should be some equivalent version of a Cheeger kind of theorem for social networks, or at least it'd be nice to know why not, right? So if you compute these eigenvectors, is that interesting, right? And if not, then that may say that this is the wrong approach for this whole thing.
I have seen Cheeger inequalities for these higher order Laplacians.
So it's already been done, so that's good.
I don't remember. Okay, I'll find the reference for you.
No, that'd be nice. Okay, good. And I think that's it. Good. Yeah. Okay, thank you.
I think we have time for questions.
More time for coffee.
Okay.
So you would expect that if you do some kind of a clustering based on this eigenvector of the Laplacian, then you get results.
Yeah, well, yeah, because somehow it's going to be assigning values to vertices, to triangles, and so then you can sort the triangles by that.
Is there an easy direction of some kind of Cheeger inequality that, I mean, Cheeger inequality is two sides, right? So one is the harder and one is the easier direction. So is it related trivially to some quantity that you are trying to optimize?
Yeah, well, that's the first question, right? I mean, is that even interesting to sort? I mean, the obvious thing is you sort the triangles by their value, right? And roughly that's what Cheeger says to do, right? And then you do something with that, right? If you sort the vertices, the triangles by that, does that tell you something interesting about the social network? I think that's the first actual question.
So Gary, I am interested in social networks, but I am, maybe an exception in this room, also interested in scientific computing. So what PDEs are amenable to this style of thinking?
Yeah. So that's why there's this other co-author, Noel Walkington, who is a numerical analyst, and we found this big, huge book. You can find very big, fat books on things like doing Maxwell's equation, because that's critical in radar, right? I mean, the critical thing in radar is you need to figure out whether there's a plane in there or whether that's, some other kind of thing, a duck. And so somehow you need to do those things. And so these calculations would be very important. But we never got enough into the book to figure it out. Other than there is this slight problem, and that is normally when you're doing radar, what you do is you have a convex ball, that's fine. But you also have a hole in the inside where the airplane is, right? And so you need to be able to work in some kind of annulus. So then there's all these nice topological questions. So what we really need to do is find 5 more co-authors that really have a good handle on topology, and then maybe we can make headway.
This issue of simplicial, nested simplicial ROM complexes and all this stuff, it's a relatively hot topic in numerical digitizations for PDEs these days. And so language they use is similar to what you were, of course, I mean, you borrowed it from them. And it's not an area I have expertise in, but I certainly have access to people who do have expertise in.
Yeah, it'd be fun to sit down with someone for which, the language, barrier isn't too big, and discuss this, right? And so that the hope is like maybe one possibility is with Noel or someone like that, be able to have sort of a 3 or 4 way conversation, trying to understand. Also, it'd be fun to bring in a topologist, because I'm not sure at a first cut they worry about, these messier kinds of questions like collapsibility and stuff like that, right? I mean, somehow I think the book that he found, there's a very big famous book on this stuff, and didn't worry about this particular aspect of it, right?
Making that regard is good also with Ados.
Yeah, until someone like Herbert involved, right?
Because 10 years ago, he's continued to make this claim, which we can't use as a condition. He basically said that any of the sliver floating to the surface doesn't matter. He just literally said that way, and he didn't explain it. Yeah. But it seems like this surface one, you can somehow peel it off. It sounds like right.
Yeah, I don't see. Yeah. So the trouble is then you look at these things like the dunce hat, which I still haven't gotten my head around, right? And it's interesting to look it up when you go online, right? I mean, there's also good YouTubes on that. But anyway, so it's just simply a single triangle where you identified all 3 sides back on itself, called a dunce hat, and that's very complicated, right? Let alone anything else, right? There's Bing's house and.
The 3D mesh that let's see, all the aspect ratio are good, except the one that you can somehow collapse. So somehow you have a chain of collapse that leads you to a new one that has good aspect ratio. Does it has a numerical stability somehow to say this is a good system?
Yeah, I don't see how just throwing in the fact that all the tets are nice is somehow going to solve the problem. I'm a little worried that it's, more subtle than that.
It's a numerical stability, right? Because the tets are nice, normally says the solution are closed. It has nothing to do with solving this kind of thing.
Yeah, but somehow we need something stronger here, right? We need, somehow, like just how do you find a flow? And my feeling is there's probably some other tricks that make this stuff work. There must be, more ideas how you do this, adding other tets or some other kind of, it's not really clear whether it hurts to add other stuff to the system or not, right? I could just imagine this is wide open. We're just not very imaginative at this point.
What should be done?
Other questions, social networks? That's probably more interesting. Let's have a coffee.